This project is about compressing ResNets for FPGAs.
This is Don Lee.
And I'm Gabriel Marcano. Neural networks are used in a lot of applications, like object identification and voice recognition, but usually require power-hungry GPUs. Field Programmable Gate Arrays, or FPGAs, are an alternative that uses less power. But FPGAs have limited resources. We need to compress neural networks somehow to get them to fit into FPGAs. One approach to compress neural networks is via a process called knowledge distillation. Knowledge distillation requires a teacher neural network effectively teach a student network how to act more like the teacher. This student network can be significantly smaller than the teacher, thus leading to a compression or distillation of knowledge from the teacher to the student. For this project, we are working with residual neural networks, or ResNets. The notable feature of ResNets is that they have residuals or skip connections that forward the output of some layers to a later part of the network. There is a promising novel algorithm that iteratively modifies the student ResNet during the knowledge distillation process. The student ResNet has its skip connections removed one or a group at a time while it is being trained, and this is supposed to yield better results than using knowledge distillation with a student with all skips removed at once. We implemented a version of this algorithm for some of our tests. So for our project, there are two parts. First, we have to train the teacher model, and then we can train the student model with help of the teacher. So to train the teacher, we have to run our training script, which takes in a configuration file describing the model that needs to be trained. In this case, we're going to train ResNet 20, quantized weights, where each weight has 8 bits, 2 of which are allocated to the integer portion of the weight. And it is now beginning to run.
The next morning.
We finally have the teacher model trained. So in the output directory for the teacher, we get information about validation losses and accuracy, training losses and accuracy, and graphs plotting those files. So for the accuracy, we see the training accuracies and the validation accuracies. The major jumps that we see here are due to learning rate adjustments, and we see that eventually levels off. And here we see the actual model. So this is the file that we're going to use as an input for training the student network.
Next, we're going to be running skip connection removal alongside with knowledge distillation to help converge the student network into getting better accuracy through the teacher model. The way to run this process is doing exactly the same process as training the teacher model, except in our configuration files, we need to include the teacher model and the amount of skips we want to remove to use the script skip.py. Skip is a iterative process. We're going to run the program multiple times, which means a longer process. Well, since this is going to be running for a long time, I'll see you guys in a bit.
A few moments later.
All right. Every one of the skip removal iteration has finally finished. Similarly to the teacher model previously done, there is an accuracy and losses graph for each skip iteration, alongside with text files that shows the numbers of the graph. Now we're getting to the good part, which is higher level synthesis. In this, we use a third-party software to convert a Python script to a lower level language. In order to run this, we would need to get a model and go off of that. Rather than using quantized ResNet 20 with 8 total bits and 2 integer bits, we are going to run ResNet 20 unquantized, and now we run it.
One eternity later.
We want to focus on how much utilization is being used, which is going to be located under my project _ project directory and under solution1 subdirectory. The JSON file will contain all the useful information regarding whether ResNet 20 is going to fit into an FPGA like BRAM or block RAM and LUTs. Thank you for listening.